Great honor and delight to introduce ramabhadran, who is a researcher at Google. Bhuvana actually spent quite a few years at IBM, T.J. Watson Research Center as a distinguished research staff member and manager there, doing a lot of very important, interesting things in speech and language processing, pretty much various problems that you would have read about, everything from keyboard spotting to ASR to any number of various projects and DARPA projects, etc. Bhuvana has also sort of been very active in our community as a leader and a role model for a lot of people, including sort of both IEEE. She led the SLTC and also as a board member in ISCA. So she's well known to everyone. Bhuvana is a fellow of IEEE and ISCA, and today, it's a perfect person to talk about some of the challenges and offer her perspectives on open problems in speech recognition. So Bhuvana, it's a great honor. Please come. Thanks for agreeing to speak.
Can everyone hear me? Yes, I think so, right? Thanks very much, Sri, for that very generous introduction. So today I'm here to talk to you about open problems in speech recognition. Many of you have published on several of the areas in the sessions of the last 2 days, but I thought it would be a good thing to recap some of the issues and challenges we all have faced over the last few decades and what we're focusing on today. So to begin with, let me first start with giving you an outline of my presentation. I'll first talk about speech recognition, how it has evolved in the last few decades, what are the areas we've focused on, what algorithms we're still carrying over no matter what the fundamental modeling paradigm is, and the applications and the programs that have influenced the various directions of research that we've seen, the current trends that what people are focusing on, and the open problems and what perhaps we can learn from the results we've seen over the last few years in not just English, but in all of the many languages we're working on. And throughout this talk, I'd like you to keep this slide in mind, which I shamelessly borrowed from the interspeech organizers. The theme of this conference is on speech research in emerging markets and multilingual societies. And if you step back and think a little bit about that and look at all the papers we see, much of the research over the last few decades is focused on English, US English. And while we have had some efforts to do other languages, the primary results, the algorithms, the focus of improving recognition performance step by step, a lot of work has gone into English over the last few decades. So, to keep things in perspective, there are a lot of products and services deployed by various companies today. You've heard industrial talks, you've seen the show and tells, demonstrations. There are languages that are covered. So they're probably somewhere between, say, 50 to 100 languages, each one with different levels of performance that you see from these products. But if you step back and see how many languages are there in the world, that would be a very tiny speck in this circle. If we say this defines the number of native language speakers, there are like about 400 languages with at least 1 million native speakers. And now we're saying we've covered speech recognition in languages of about, say, in the order of less than 100, give or take, right? So we have a long way to go there. And if you take a little bit broader view, you'll find that there are like 1,342 languages with at least 100,000 speakers, native speakers of those languages. And if you look a little bit further, there are like 3,150 languages with at least 10,000 speakers. And all we've done is addressed a very small set of these languages, and we have a very long way to go, and many of these languages are spoken by maybe as few as 50 people. And there's a big, large billions of users there that we would like to reach. And that means we have to focus a lot on these emerging markets and multilingual societies, and that's something to keep in the back of our minds. So let me begin by talking about the way speech recognition has evolved in the last few decades. And there are a few things to keep in mind. This is time on the x-axis and word error rate on the y-axis. And you see how in the beginning, in the early 90s, when people started to work on this English conversational telephony task, the error rates were pretty high. You know, we're like in somewhere between 60s and 80s. And if you think a little bit, we're still that way when we start to work on a new language. Even though we try all our techniques of initializing with whatever data we have and the best models we have, we still start at a pretty high point, and then we adapt, we add all of the methods we know and get to a reasonable level of performance, right? So I've broken this down into like 4 categories. What were the single biggest wins we saw over the decades as we went along? The first biggest win came from adaptation, speaker adaptation, MLLR, any type of feature transforms that you could do to represent the speaker, noise removal, and so on. And that pretty much brought us down in the word error rates down to about half of what we were starting at. So that was a single big contribution that helped us improve speech recognition, right? The next biggest thing came from improved HMM training. We had all of the discriminative training methods that came into existence. MCE, maximum mutual information-based training, and then you had a minimum phone error rate-based training, the minimum word error rate-based training. All of these methods help to compensate for the lack of data, which otherwise maximum likelihood approaches would have taken care of. And we found that focusing on these discriminative training approaches helped us cut the error rates further by half. So we're now in the 20s on the same task where we started very high, like in the 80s. These 2 kinds of fundamental contributions still hold today. The next big jump came from the evolution of neural networks. So around 2010 or so, when there was a rebirth of neural networks, that was the single biggest impact of what's known as deep learning today, right? So we had different variants of neural networks being used for all of the large vocabulary tasks. It was first introduced for the story problem until then, and then later on extended to by various people, various industry players and academia to work on large vocabulary tasks such as switchboard that I'm talking to you about. And then more recently, in the last 3 or 4 years, we've been focusing on complex architectures. How can we add more parameters to the network? Convolutional networks, LSTMs, because they have a long-term memory, and in terms of saying, can we add more layers, such as BGG networks, like up to 19 layers. Some of it borrowed from the vision community, some of it that we have adapted to work well on speech because of the complex nature of the speech problem we're looking at. But we seem to be going in the direction of how can we combine many systems, complex architectures, and that seems to be moving our word error rate even below the level of human performance. So the 5% line you see here was a study done by a couple of research groups at IBM and Microsoft, and where they showed that human performance on this task had a 5% error rate, give or take. And many of these complex systems that were put together could reach that performance or even slightly better. And again, on this English telephony tasks. Now, one thing I didn't cover when I talked about all of this is how much data was there between 1990 and between where we are today. So perhaps when Switchboard was first started, we started with like 5 hours, 50 hours, so on, but 300 hours is considered pretty much a standard Switchboard corpora to work with. And then now we have about 2,000 hours of the Fisher corpus augmenting that, not necessarily manually transcribed, but along the way we've also increased the data by tenfold. It is a rough way of looking at these things. So 2 things to keep in mind is how much data has grown, what can we do if we have very little data, and also what is the pattern of evolution, and this seems to be the same no matter which language. I could produce a graph for you in Arabic, say, which looks exactly like this, or in Spanish, which we worked on as part of a European Union project, which also looks very similar. The trend seems to be the same, right? And also if you look at some of the neural network methods we see today, the adaptation and the discriminative training approaches that seem to give a very nice win with the HMM approaches are the ones that we still use in the complex architectures and in many of the neural network models that we deploy. So we're constantly learning from previous traditional methods and incorporating them in new end-to-end models. And we focused all of our research on pretty much one language. Yes, there's effort in other languages, but not to the degree that we've seen in this English task. So keeping this in mind, let's take a walk down memory lane, if you will, on how we've gone from GMM to the various flavors of the neural networks. We shouldn't forget that this was first introduced in the 80s and 90s, but it didn't really pick up then because it was extremely slow and relatively poor in performance compared to the state-of-the-art GMMs and HMMs. There are numerous papers published on this by ICSI, CMU, and EDAP several decades ago. And one of the key attractions of these neural network models were there was no assumption made about a specific distribution of the data, and parameters could be easily shared across all of the data. Even today, these complex neural networks are slow to train, so they limit researching with these ideas on really large tasks if you have tens of thousands of hours to train. Nevertheless, we've still seen an extensive use of these ideas on using various complex neural network architectures for large vocabulary tasks. How are we using these neural network models? We're all familiar with GMMs, and in neural networks, we can use them both for acoustic modeling as well as for language modeling, right? And in acoustic modeling, most approaches still use it as the neural network model to derive a posterior probability of an HMM state given an acoustic observation. And the advantage of doing this was we could all use our existing HMM speech recognizers and just plug in a neural network instead of the Gaussian mixture models that we were using before. And during recognition, we use the Bayes rule to get the class conditional probability. Now, this model is known as the hybrid neural network HMM model, and it was originally introduced in '93 by Goulart. And we still use this for the hybrid NN HMM model that we use. Now, if we think about how we use this in the language modeling scenario, most probably we're all using neural network models in a rescoring framework where we rescore a lattice, or we're using them in the first pass where we represent the neural network as a conventional n-gram model so that you can easily compute in real time the scores needed for the words and in order to get your first hypothesis. The use of neural networks for language modeling was first introduced by Bengio in 2003 and then extended to LVCSR tasks by Schwenk. And subsequently, we've seen its use for syntactic-based language modeling and then to derive word embeddings, semantic word embeddings, sentence embeddings, and what have you. There's also been work focused on reducing the computational complexity. And in order to do that, people have done approaches where they have used a short list of candidates at the output layer and a hierarchical decomposition of the output probabilities and, of course, recurrent neural networks for deriving many of these embeddings. And I've referred to some of the work here. It's not exhaustive. There are 3 pages of references at the end of this talk if anybody's interested. But this is just to give you a flavor of how we've evolved and how we've started to apply neural networks to acoustic and language modeling. And 3 main components stand out in the process of applying these neural networks. One is the training objective we used. Originally, people were using the mean square error criterion because it was very robust to outliers. And later on, they realized that they could use the cross-entropy criterion, which relates better to our maximum likelihood philosophy that we're all used to. And because the MSE criterion has several plateaus, it was difficult to optimize, so we moved on to the cross-entropy criterion. And also, there was nice theoretical reasoning behind it that if you didn't have hidden layers, it was a convex optimization problem, and the softmax reduced to just a log linear model, and we could derive all sorts of interpretations from that. That evolved into using sequence classification criteria, which closely related to what we were used to in the HMM discriminative approaches, where we did things like minimum phone error rate type criteria. We call them the minimum base risk criterion. You could use any sort of loss function there, but it was a discriminative type approach. So even in the neural network paradigm we've used, we've borrowed upon from several speaker representations, several training objective functions, and this is one of the key things researchers focused on over the last few years. The next big thing is the optimization. How do we train these networks? How do we estimate their parameters? What are the algorithms that we use that will enable it to scale to these large vocabulary tasks? Gradient descent, which is well known, still works practically for most of the applications, But there are other sophisticated algorithms that exist which are an alternative to gradient descent, many of them using second order terms. But people have sought to look at things which automatically tune the learning rate, which tune the batch size, and which can be parallelized. People have found ways to approximate the Jacobian, approximate the Hessian matrix so that we can take rapid steps towards the local optimum. And I've listed some of these algorithms here, like LBFGS, conjugate gradient, ADAM, and so on. And while this sort of optimization has been happening, there's also been a focus on reducing training time, because we can't wait for months to figure out if one particular network architecture is going to be any different from another. And this particular reduction has come from evolution of hardware. We've had GPUs which have gotten better over time, and these have helped us do matrix computations really fast. Distributed training and asynchronous methods of SGD have picked up. And also Hessian-free training on multiple GPUs, to the range of massively parallel hardware such as Blue Gene, which IBM used, or specialized tensor training hardware such as TPUs you see in Google. So there's a spectrum of activity here, and a lot of papers which address some of these benefits of one sophisticated algorithm for computing the gradients and updating your parameters to reduction in training time. So we have training objectives, the optimization, and a lot of work on what would be the input and output of these networks. What are we going to give the neural networks to learn from, and what are they going to predict? So in the front-end side of things, whether it's if you're learning an acoustic model, if your neural network is an acoustic model, you could either start training it from a raw waveform, the MEL spectra, raw spectra, PLP. The networks can learn the MEL filter representations. Can they learn the speaker representations? Can you feed in a vector, which is a speaker representation, which itself could be an embedding from a neural network, or it could come from a Gaussian mixture model. So these are all various acoustic front ends that have been tried. Two, in the case of language modeling, where you typically give word histories, word counts, class histories probably, additional linguistic information like meta information relating to part of speech, and also embeddings, right? And all of these networks predict, in the case of acoustic state, in the case of an acoustic model, a context-independent phone target, or just phonemes or graphemes or characters, or even segments or combinations of these. And in the case of language modeling, you're predicting words or subword units, fragments, or characters or combinations of these. So you have a diverse spectrum of input-output representations, training objectives, and optimizations, and this is a huge grid search across these to determine for a particular task what is going to be the best possible combination or representation. So there's been a lot of effort put into this for English and now in other languages, but every time we take a new task or take a new language, we find ourselves starting from scratch again, pretty much. We learned from the previous methods, but we're pretty much retuning, fine-tuning many of these methods. So it's another thing to keep in mind as we move forward with what are we going to do with a multilingual society. So how many hours of data do we need to train an ASR system? That's the question we begin to ask ourselves, right? Because when you go to a new language, the rule of thumb generally is if you have 200 hours, you should have a reasonable ASR system. Switchboard system at 300 hours on English was giving us a performance around 20%. But what would you do if you only had 40 hours? Or what would you do if you just had 3 hours, which is just a tiny speck? And that's pretty much the amount of data that's available in many, many languages. And these are good things to keep in mind and see how you can use data from other languages or what you already have in going forward with a low resource language. And that led to one program sponsored by IARPA called the Babel program, which many people in this room worked on. And the goal of the IARPA-sponsored project was to rapidly develop speech recognition capability for keyword search specifically in a previously unstudied language, working with speech recorded in a variety of conditions and with very limited amounts of transcription. And the project focused on 27 different languages. Every period is a year, and every period a new language was added. And it also focused, as it happens to be, on 4 Indic languages: Assamese, Bengali, Tamil, and Telugu. And if you looked at the way the error rates evolved, I'll show you some numbers, not too many. They all pretty much followed the same pattern as the English graph I showed you earlier. But even if you had just 3 hours in one language, we had 27 languages to take advantage of, and anything else that we had. And all the partners and participants of the BABEL program developed neural network methods and other methods that could take advantage of this. And one of the key things that came out was multilingual representations. Multilingual representations are something that we call as features extracted from a neural network of any kind. What I'm showing you here is a two-stage neural network, and this is a bottleneck layer from which we extract the representations. Each of these networks have been trained on all of the languages. So the bottom layers have seen every language and its corresponding output targets, whether they were phones or context-dependent states. And the multilingual representation derived from one layer was passed to another network with additional context. And a final bottleneck representation was extracted called a multilingual representation. And you could do what you wanted with these. You could build a GMM model, you could build another simple feed-forward network, and you would use that to produce lattices or whatever representation you wanted in order to do keyword search. And these networks, I'm showing a very simple block diagrammic representation, but they could be your VGG network, which had like 19 layers of convolution, or it could be 5-layered bidirectional LSTM. Plug in the favorite variant you have, and the network was capable of extracting a feature that spanned the acoustic space of all of these languages, and you could use that intelligence that the neural network captured for a new target language that only had 2 hours or 3 hours. And if we look to see what happened with the performance, I list some of the languages here. And this is if you just use your traditional feature representations like PLP, what have you. But if you use the multilingual representations, you see there was a substantial improvement. Yes, the error rates are still high. They're still in the 40s and 50s. But still, there was a big difference between 80 and 40. And that's what the multilingual representations took the performance of many of these languages. So that was one thing to keep in mind in the evolution of speech recognition, that we learned that we could extract representations that would better represent the acoustic space of a language of which we have very little data. Now, some of the current trends, as you would have seen in the last couple of days, has been focused on sequence models, or the class of sequence models. We're so used to optimizing cross-entropy criteria, or the SMVR, the language models for perplexity and computing word error rate. What if we could avoid the need for explicitly computing alignments and allow for more sophisticated sequence models? Perhaps we can do away with HMMs. That was the thinking in this evolution of these sequence models. And there are two broad approaches that you're all familiar with. One is the CTC, and the other is the attention modeling approach. The CTC solves the problems of alignment by taking any input sequence, length of any input sequence, and aligning it with whatever your label target sequence label should be, by marginalizing out the conditional likelihood of the output sequence given the input over all possible alignments. And the attention model does a simultaneous optimization of the alignment as well as the classification of graphemes that you're looking forward to doing. And both of these models work well in the graphemic space, which lets you ignore the fact that you would need a lexicon, which is another major expensive source for a new language. So just to say a little bit more about CTC, the CTC loss function was introduced by Alex Graves in 2006, and it was defined over a labeled sequence, say of length m. And the idea was to automatically align by summing up over all possible frame alignments of length d with the permitted label sequence using a forward-backward output. That was the CTC loss function. And it introduced a blank symbol to allow for these various possible alignments. Now, most of the time, the network would put out the blank symbol, so it's pretty sparse. And if you look at the end-to-end attention models, of which there are several variants, you've heard about the listen, attend, and spell model, you've heard about other forms of encoder-decoder models. The attention machinery is a function of the previous attention activations and the encoder activation. So the encoder is now encapsulating all the information that you can extract from your input signal, which is your audio features. And the decoder functions like somewhat like a language model and helps it to predict these graphemes or the blank symbol. Now, while the CTC model was designed to do frame-level posteriors, the attention model will just generate its predictions until it hits an end-of-sequence symbol. So you need some way for it to stop predicting, as well as for it to not babble on. The well-known issue with both these models is they have very short posteriors, which means if you're looking to do lattice rescoring with a better language model, or do keyword spotting, you're going to end up with very thin lattices. And that also puts you in a direction of what are we looking to do with the output of ASR? What is the subsequent NLP task that is going to follow? Is it a conversational system? Is it a translation system? Keyword spotting system? Because then at this point, while these models improve word error rate and they're fancier, complex models, they are now they're handicapping you for the next stage. So you start to introduce other approaches, other methods like whitelisting to augment them further. So whatever you were doing earlier in the front side, now you're attaching at the back side to take care of the long tail distribution. So it's all a balance, and depending on the task and the language, one model may work better than the other. So the Babel program also produced novel architectures and novel ways of thinking. So that since the problem was keyword search, one question that was asked was, do we really need to do ASR to do keyword search? Now, this is not a new question, but given that we had all this complex machinery at our hand, we could think in terms of, you have your audio database through which you're looking to, you could segment it into sentences and derive sentence embeddings, which is what this does with the fancy end-to-end system. You could extract a word embedding from the query you're looking to search in that database, and you could have a third network which would decide whether this embedding was part of this embedding. How well does this work? This seems to be like a very free-flowing model with free parameters, and it can go any way. But surprisingly, it does almost to 70% accuracy. I would have expected something like 50% because it could be pretty random, there are a lot of variations, but the model does pretty well. How do the sequence models perform in the Babel languages? So I'm not going to go through this in detail, but if you look at some of the same languages and you say, here are the multilingual representations, you saw this before, these are the frame level, you have CTC at the frame level, and you have the attention models. They're all pretty much on the same. In some languages, one may be slightly better than the other, but these new models, when you have the kind of data that the Babel program had, performed all about the same. And we pretty much see this in other languages with lots of data as well. But we have ways to tune them to do better and edge out the models we're all used to. And then moving on to what do we understand about neural networks? Many of you are familiar with this picture from the vision community, where it's understood that the input representation of pixels is at your bottom layer, and as you proceed through your neural network, you learn different parts of the image you're trying to predict. So for example, you may start off with some edges, then you predict the object parts, and then you move on to the full objects. So there's some level of interpretation we can put in at each of the hidden layers. And we've extended this to the speech recognition problem as well. And you've seen some work where we talk about the hidden layers extracting phonetic clauses or speaker representations. There was an interpretability workshop earlier today which also talked about what kind of representations do these layers learn. Now, why is this important? At least in my view, the most important challenge that needs to be addressed is we need to understand what these networks are learning. We need to be able to interpret these hidden representations so that we can build models that would be more robust to noise, which they still are not. Far field is still a big problem. Speaker domain adaptation algorithms that can be enhanced if we knew what portion of which hidden layer to adapt in which way. And remember, we're always coming from the same ideas we had earlier about adaptation, distributed training, and bringing them over to neural networks. It would help if we could bring some of those to certain specific areas of these networks. And another important thing to keep in mind is switchboard is at 5%, but meeting transcription is still bordering around 40. And all of the other complex acts in other languages are still bordering around that range. So I think it's important to focus on this problem and also relevant metrics to measure performance of these models. We talked about code switch languages today. Umesh, in the beginning of the opening ceremony, talked about combinations of English with other languages. We need to be able to separate the modeling problem from the rendering problem. If we could model everything in one space and figure out how to render it based on the task at hand, it would be a much easier task for us. And we have a paper in SLC talking about this. Could also lead to the question of, can we have a combined recognizer that works just as well as it did in switchboard across all of those languages? So a few small steps in that direction. There have been lots of frameworks that are existing today which still work across, multiple targets, whether it's text or whether it's speakers for the identification, separation, etc. Multitask objective functions and joint modeling with these complex networks on ASR NLP tasks. So that's one step in the next direction I think we should all be looking at. And with that, I'll leave you with a few points to focus on. Never to ignore the big picture, and you need to see what the impact of ASR improvements are going to do on the subsequent tasks. Like in Babel, we got improvements in word error rate, but it didn't necessarily mean it would impact the keyword metric. So that's something to keep in mind. We should never ignore the implementation aspects, because when you start reducing or taking approximations for speed and memory consumption, you would end up with very different conclusions. The fancy algorithms may not be that fancy anymore. And it's very important to work out well benchmarked and studied corpora so progress can be tracked, as the case with switchboard. And it's always important to ask, is there some motivation, linguistic, theoretical, that we can extract from these models? Because that could lead to simpler architectures, and we could be more robust to personal examples. So that's all I have, and I'll leave you to think about some of these points. Thank you.
Thank you. So we are running out of time, actually. Since we have the ISCA assembly, General Assembly, at 5:30, we don't have time for questions at this point. So catch Bhuvana, who's running around during the conference, to ask all your questions about ASR. Sorry, we don't have time for questions this time. But we do have time to give Bhuvana this thanks box. Thank you, Bhuvana.